Good morning all. This is Satish Kumar, Assistant Professor of EC Department. Now let us see the another video lecture series on linear time invariant system using Fourier transform. See, linear time invariant system are characterized with the help of differential equation, impulse response, block diagrams, state variable description and transfer function. Differential equation, it's used to represent the linear time invariant system. It relates the input and output of the system. When the x of t is given to the differential equation, which can produce the output as y of t. The system transfer function is nothing but ratio of the output to the input. H of s is equal to y of s divided by x of s. Frequency response, s can be replaced by omega. Therefore, h of omega is equal to y of omega divided by x of omega. When the input function is applied to your Fourier transform, we can get the output as x of omega. That can be applied to the frequency domain analysis. We can get the y of omega. While taking inverse Fourier transform of y of omega, we can get y of t. The condition for a linear time invariant system to be causal is nothing but h of t is equal to 0 for t less than 0. Linear time invariant system to be stable, summation k is equal to minus infinite to plus infinite. Modulus of h of k should be less than infinite. The impulse response is nothing but is the output generated by the system when the unit impulse is applied at the input. X of t, when the unit impulse function is applied to your input of LTI system, which can produce the output as h of t. Del of t is equal to 1 for t is equal to 0, 0 for t should be not equal to 0. H of s is equal to y of s divided by x of s. How to find the impulse response system? While we taking the inverse Laplace transform of system transfer function is nothing but we can get the impulse response of the system. Fourier transform. Fourier transform can be applied for both periodic and non-periodic signals. It can be represented in frequency domain. It provides the effective reversible transformation link between the frequency domain and time domain representation of the signal. The spacing between the spectral components becomes infinitesimal and hence the frequency spectrum appears to be continuous. Periodic signals has a fixed time period t0. This is the analysis. While we taking the time domain function for analysis, we can get the frequency function, that is nothing but s of f, right? While we for the f of a function, we can taking the inverse Fourier transform, we can getting the s of t. S of f and S of f forms the Fourier transform pair. This is the periodic impulse train, minus 2t2 plus 2t minus 2t minus t for the time domain representation. While taking Fourier transform of the above function, we can get it as your minus 4 pi by t minus 2 pi by t2 plus 4 by t with respect to omega. This is the frequency domain representation. Next one, how to find the impulse response of the system for a given differential equation. We can apply the Fourier transform. For that Fourier transform, we can find out the algebraic equation and then solving for roots. Finally, we can taking the inverse Fourier transform of the above function. We can getting the impulse response of the system. This is the periodic symmetric square wave for sin omega naught of t, cos omega naught of t. For that above function, we can taking the how to find the frequency response. This is the frequency representation of the periodic symmetric square wave. Next one, properties of convolution integral, commutative, distributive and associative. X of t multiplied with h of t, which is equal to h of t multiplied with x of t. Distributive property means x of t multiplied with h1 of t plus h2 of t, which is equal to x of t into h of t plus x of t into h2 of t. This is the graphical representation of distributive property. Next, associative property, x of t multiplied with h1 of t again multiplied with h2 of t, which is equal to x of t into h1 of t into h2 of t. This is the graphical representation of the two x of t multiplied with h1 of t again multiplied with h2 of t, we can get the y of t. X of t multiplied with h1 of t into h2 of t, which can produce the output as y of t. This is the basic signals, unit step signal. It has an amplitude of 1 for t greater than or equal to 0, 0 for t less than 0. Unit impulse function, del of t is equal to 1 for t is equal to 0, 0 for t should be not equal to 0. Unit ramp function, r of t is equal to t for t greater than or equal to 0, 0 for t less than 0. This is the graphical representation of unit step function, unit impulse function and unit ramp function. Next one, how to find the Fourier transform of x of t is equal to u of t. X of f is equal to integral over minus infinite to plus infinite x of t into e power minus j 2 pi f t into dt. U of t is condition is 1 for t greater than or equal to 0. We can take the limits from 0 to infinite. We can get the x of f is equal to 1 divided by j 2 pi f. Fourier transform of unit impulse function is nothing but anything taking from the for unit impulse function, we can get del of t is equal to 1 for t is equal to 0, 0 for t should be not equal to 0. Therefore, x of f is equal to 1. Next one, the system produces the output y of t is equal to e power minus t into u of t. For an input x of t is equal to e power minus 2t into u of t. Determine the impulse response and the frequency response of the system. Y of t is equal to e power minus t into u of t. Y of f is equal to 1 divided by 1 plus j 2 pi f. X of t is equal to e power minus 2t into u of t. X of f is equal to 1 divided by 2 plus j 2 pi f. Therefore, h of f is equal to y of f divided by x of f 2 plus j 2 pi f divided by 1 plus j 2 pi f. How to find the impulse response? H of t is equal to Fourier inverse of h of f. Therefore, Fourier inverse of your above function, we can get h of t is equal to del of t plus e power minus t into u of t. The differential equation of the system is given as d square divided by dt square into y of t plus 5 into d by dt into y of t plus 6 into y of t, which is equal to minus d by dt into x of t. Determine the frequency response. It can be d square divided by dt square can be replaced by j omega square. J omega square into y of omega plus 5 into j omega into y of omega plus 6 into j omega y of omega, which is equal to minus j omega into x of omega. Now we can take y of omega, we can take as common as outside, j omega square plus 5 into j omega plus 6, which is equal to minus j omega into x of omega. Therefore, h of omega is equal to y of omega divided by x of omega. Therefore, minus j omega divided by j omega square plus 5 into j omega plus 6. Now we can see the assessment. The system transfer function is given by h of s is equal to y of s divided by x of s. DAX relates the input and output of the system differential equation. What does mean by impulse response? When we giving the impulse response to your LTI system, which can produce the output as h of t, that is nothing but impulse response. Define unit step and unit impulse function. Unit step can be defined as u of t is equal to 1 for t greater than or equal to 0, 0 for t less than 0. Unit impulse signal del of t is equal to 1 for t is equal to 0, 0 for t should be not equal to 0. The condition of an LTI system to be causal is given by h of t is equal to 0 for t greater than 0. Fourier transform of unit step function is given by x of f is equal to 1 divided by j 2 pi f. The condition for stability of an LTI system is summation k is equal to minus infinite to plus infinite. Modulus of h of k should be less than infinite. Linear time invariant are characterized with the help of block diagram, differential equation, transfer functions, etc. Thank you.